This lesson is on factorials and permutations. So the previous unit we covered fundamental counting principle, which is, as the name suggests, very fundamental. In fact, you can use that for virtually everything in this entire unit, virtually everything. However, we do develop faster, quicker methods for dealing with certain types of questions, which do not mean that you should forget about the concepts of the fundamental counting principle, but you should choose wisely when you can use a quicker method. You'll see what I mean as we go further into this. Now, let's start off with this question, pretty routine looking one. Milton has 5 different books and he wants to arrange them on a shelf. Now, I know you're thinking, well, upside down, backwards, on the facing, all sorts of little things you could do on a shelf. But in fact, if you take this in its most conventional meaning, it would mean that he's just going to put them up beside each other, and it would mean that he would have 5 choices for the first position. 5 books could go there. Now, the type of question suggests that it's a concrete object, so it's an object that cannot occupy more than one place. So that means once it's seated in one place or positioned in one place, you can't repeat it. So you always want to be aware of that, whether repeats are allowed or not, and it's usually in the question itself. Even if it's not stated, it would be strongly suggested by the nature of the object in question. And then this would go down for 3 choices for the next, 2 choices for the next, and then 1. And according to what we know about the fundamental counting principle, we would just multiply them out. And that would give us 120 different ways. You're probably thinking, however, well, that's fine if you only have 5 books, but what if you have 20 books or 30 books? Who wants to be multiplying it down every time they're going to arrange books on a shelf? And this is where the factorial comes into play. So if we use factorial notation, or the factorial feature on our calculator, then we can shortcut this. And the factorials work like this. 5 factorial, that's sort of exclamation mark, would take the number 5, which is the number of books Milton has, and would multiply down in descending order like that. So 5 times 4 times 3 times 2 times 1 until you got right down to the bottom. So 6 factorial would be equal to 6 times 5 times 4 times 3 times 2 times 1, just like that. And because this feature exists on your calculator, in fact, in almost every scientific calculator for the last 25 or so years, you can, instead of multiplying it down by hand, you can let the calculator do the work for you. Now, on your calculator, to find this key, some calculators, the little handheld small calculators, tend to have it right on the display, so it's easy to use. Most graphing calculators have it have the menu elsewhere, which requires a little more work to get to. But you press, to do 5 factorial, you press 5, and then you press the math key up on the left below the green alpha key, that is on the TI-83. And then once you're in the math menu, if you go to the right, you can take it to the probability. Now, by the way, you can also go to the left and just go 1 over to the left, because your calculator will do a wraparound, and then you'll get to probability. And once you get to the probability menu, you'll see we have a bunch of things, some of which we will be using in this unit. But the first one would be number 4. So you either press 4 or you take your cursor down there and press enter. As soon as you do, you should get, let's back this one up, you should get equal to 120. Then you've got it. In general, a factorial, n factorial is equal to n times n minus 1 times n minus 2 times n minus 3 all the way down to 1. So it's just descending values. Always whole numbers. There's never any fractions or decimals or negatives as well. And 0 factorial is equal to 1. Now that's sort of an oddity, but you'll see later on why it has to be that way. It's rarely an issue, but it doesn't really make sense seeing as we're starting at 1. So just make a little note of that, and it'll sort of reappear later on in a very limited way. So that's a time saver. Now the next time saver is the permutation concept itself. So this is important In a permutation, the definition is an arrangement of concrete objects in a definite order. Now, I inserted the word concrete. It really is redundant. When you say it's an object, that implies that it occupies space. But I want everybody to be clear that we are talking about fixed objects. So it implies that there's no repeats. So if you are seated here, you cannot be seated somewhere else. It implies no repeats. And mathematically, it's based around that. Implies no repeats. So there are n factorial permutations of n objects. So if you have, like in Milton's case, 5 books and space for 5, it is 5 factorial, but we could also use permutation methods for it as well, which I will introduce right now, or in the course of this question, excuse me. So here we are. Trixie has 12 books, but space for only 8 on the shelf. So she's got a real dilemma. In how many ways can she arrange them? Well, you don't need to know anything about factorial or permutations, because all you need to use is the fundamental counting principle and just set it up like this. Trixie will choose 1 of 12 books for the first position, 1 of 11 for the next, 10, then 9, then 8, then 7, then 6, then 5. And the thing of it is, you cannot use your factorial key with this one, because your factorial key will take you all the way down to 1, and we don't want to go that far. So we have to multiply this by hand, and that will give us 19958 400 ways. So lots of choices. If you're really on the ball with this one, you could figure out a way to use factorial. And this is in the old days. This is how we would deal with these before we had permutations programmed right into our calculators. We would take that 12 factorial, knowing full well that it would take us all the way down to 1, but then we would simply divide away the ones we didn't want, which would be 4 factorial. So you could do this, 12 factorial divided by 4 factorial. So you divide away the ones you don't want. And make sure you divide. Some people instinctively subtract because they think that they're just sort of using an indirect method. But you must divide because those are being multiplied together. Subtraction won't undo the multiplication. Now I'm going to bring up a new screen and then change the approach on this, or bring up a clean screen. The other method that we could use besides that would be permutations. And this is read as 12 pick 8. So 12 objects, and this will all be defined on the next screen, picked 8 at a time. So in other words, we have these 12 objects around, and we are going to select 8 of them. So I'll bring up a screen and actually have the math on this one, or the calculator. If you did want to use your calculator, which you probably would, we find the pick key in the same spot as the factorial key. So you press 12 first off, then you go into your math menu, take it to probability either to the left or to the right, and once you're there, you'll see it. It's number 2. So either press 2 or go take your cursor down there and then press Enter. If you do scroll down, if you press 2, you're okay. And then what happens? You'll get the same. You get the same answer. So you'll get equal to 19958 400. So it's a little quicker, particularly when you've got massive multiplication to do. Now most of you, and I would really encourage you to do so, will still set things up according to the fundamental counting principle. But when it gets right down to the actual calculation of it, you may well choose to use your pick key. The actual definition of these will come right now. In general, n pick r represents n objects picked r at a time. So the n would represent the total number of objects, and the r would would be the number that you are selecting. It always implies concrete numbers. Again, there's no repeats. And this is on a formula sheet. n pick r is equal to n factorial divided by n minus r factorial. And this is interesting because it refers back to the previous example. Now, your calculator does this for you, although there are a few algebra questions that will require it. But normally you don't have to worry about this too much, except for those type. If you think back to the previous example, when we had 12 pick 8, this would have been equal to 12 factorial, n factorial, all divided by 12 minus 8 factorial, which is 12 factorial divided by 4 factorial. Now that should look familiar because that was that shortcut that we used to do. And it was just based on this idea. So it's not a very sophisticated formula. It's just a way we can break these ones down. Let's do a question. How many permutations of 5 people in a straight line can be made? So you've got these 5 people, and we're going to arrange them in a line. So again, it's not helter-skelter. We've got spots for 5 of them. Now the way to tackle this question that I really recommend that you at least start off with is with fundamental counting principle. Draw these slots and ask yourself how many choices for the first position. Oh, sorry, let's back this one up. So we would have 5 choices, 4 choices, 3 choices, 2 choices, 1 choice. And that is equal to 120. You can check it, but I know because we just did these ones a few minutes ago. And that would be fine. Setting it up like that's a great idea, but then you might decide, well, hang on, because I'm going 5, 4, 3, 2, 1. Why not just go 5 factorial, which is also equal to 120? And then you may be thinking, well, why not go 5 pick 5? Because that's what it means, right? 5 objects, and I'm taking 5 of them, picking 5 of them, excuse me. Now, the third method is the most awkward. I would certainly not recommend it. I think that the first is the best. I would really encourage you not to over-rely on the pick key and just use factorial when it's appropriate to save you some steps. But the fundamental counting principle will force you to understand the question, which is really what it's all about. Let's try a few questions. How many permutations can be made of the letters of the word factor? So to set this one up, the long method, which I like, is to see that we have 6 letters. So we're taking arrangements of them. So we have 6 choices for the first one. And in these ones with permutations, there's nothing in it that would suggest that the words that the arrangements have to make sense. So 6 times 5 times 4 times 3 times 2 times 1 is equal to 720 permutations. And just to remind you, until you're sick of all this, this would be reasonable to go 6 factorial, or go 6 pick 6, which is the least recommended of the 3 methods. Now, to make your life a little bit easier, I would really encourage you to memorize some of the common factorials. As we know, 0 factorial is equal to 1. You don't use that one much. 1 factorial is equal to 1. 1, just 1 by itself. 2 factorial is 2 times 1, so that's 2. 3 factorial is 3 times 2 times 1, so that's 6. 4 factorial is just 6 times 4 is 24. 5 factorial is equal to 120. Then 6 factorial is equal to 720. And probably stop there, but that'll take care of an awful lot of ones. And it does make the calculations much easier because it is so awkward to be going back and forth on your menus, although there are other shortcuts you can use too. So try to remember those and you'll have an easier time of it. Let's try another question. How many 3-letter permutations can be made using the letters of the word Tuesday? So this time it's just a three-letter arrangement that we're making. So we can just draw the three slots. And we have 1, 2, 3, 4, 5, 6, 7 choices for the first one. So with the fundamental counting principle, we would go 7 choices for the first. We would have a choice of 6 letters for the next, and then 5. And then we could multiply them together, and we should get 210. So 210 permutations. In this case, however, the factorial would not work because we'd be going all the way down. So the pick method would be 7 pick 3, and we'll get the same answer. So the choice is really yours, but as I said, relying too much on the pick key and then the choose key, which we work on later on with combinations, can sometimes get you into trouble. There's no substitute on understanding the question because that's really what you're being tested on. But I'll stop right there, and then the next lesson will be on just restrictions and more complex types of setups. Thank you for your time.